this is where we left off. The three terms, don't mix them up even though they're somewhat similar. We've already discussed the uniform hashing assumption last time. Here is it's written up again slightly more formally. We have elements that are inserted, and we don't really know what their values are. All we care about is the hash sequence. So in the order that the elements arrive, we apply the hash function to each of them. And the assumption called the uniform hashing assumption just says every possible sequence of hash values, all m to the n possible sequences, are equally likely. And one way to read this is, hold on, there's no dependence on these input data elements x1 to xn, really. The hash values are computed from them, fine, but we just post hoc assume they're equally likely. So nothing in the data structure under this assumption may depend on the input data itself, apart from their number. And so we might as well forget the data entirely and look at a mathematical abstract model of the situation that's a bit cleaner to study. And we'll briefly recap what can be said in this model. That's the balls into bins model. And the name is what it does. You throw n balls into m bins. Now I'm picking the parameters here so that they match the hashing application that I always have in my mind when I think about balls and bins, or the balls into bins model. For some obscure reason, the literature always swaps n and m. If you look up results in some book, almost always you have n bins and m balls, and I find this infuriating. So I'm just gonna drop that convention and swap it around. It's always going to be n items that we insert, and the hash table has to be of size m. That's kind of a law of physics to name that m. I don't know. I'll stick with it, and there's no inconsistencies on the slides, hopefully, but if you look up in books, take care of this. Because we have this uniform hashing assumption, the ball I, whichever one it is, independently of all the other balls, finds its bin uniformly at random. So if you wanted, you could give the bin of the ith ball, could give that a name. And we can use our notation to say that this is uniform in the available bins. Okay, now I tried to write so clean and neatly and properly. Let's do this here as well. That's a way to write that assumption. It's a convenient abstraction from what actually happens. We normally think of hash tables, or I think of hash tables as the prime application of this. But you can model other things as balls into bins scenarios. You can also use it for modeling M servers and N are clients or jobs that arrive, and you have to load balance the jobs on the servers. Then you could just uniformly at random pick a server each time. That's one assumption that you could try to make, and then analyze what the system does. And many other situations where you have this this kind of model that can tell you something about the performance. It is a bit optimistic in that it makes this strong assumption that everything is independent and uniform. And so you should keep in mind that for hashing, it is almost the best imaginable case, and maybe a bit optimistic to assume it. On the other hand, if you take good hash functions in a practical sense, things that often are used for constructing string hashes, and I'm not talking about cryptographic hashes here, just fast hash functions, this murmur hash and some implementations. We won't get into the details. These are all heuristics, but they tend to work on the kind of data that people apply them on. They tend to work out to be almost like this uniform hashing assumption. So often you get results that are not completely only in theory land. But it's a bit of a heuristic, and if the data is adversarial, you can't rely on it. Now let's think about this model briefly, and even if you've seen it before, I want to point you to some slightly to a head-scratching moment, maybe. Throughout, that's the last bit of notation for now. You can forget about bi. I'm not going to use that much, but xi is the number of balls in bin I. I should have called that j. I think I'm using j for the bins most of the time. That's just the number of balls that fall into a specific bin. We have our m bins. Now these are all equally distributed by assumption, and they're all binomial because every ball independently of the others decides where to fall. So every specific bin that I'm looking at has a 1 in m chance of getting the ith ball. And so in total it has a binomial distribution with parameter n and 1 over m. So again, this is really only true under this strong IID assumption. But if you do that, then it's a binomial distribution. I've talked at length about this in previous chapters, that they are highly concentrated. In particular, we have these Chernoff bounds that say these guys are going to be very close to their expected value, right? Now, let's simplify things a bit and get rid of a parameter. We set the number of balls in bins the same. That's often the kind of starting point for analysis, just to make life a bit easier. The expected number of balls per bin is just 1, right? That's the expectation of the binomial distribution. N times p is 1 over n. At the same time, let's count how many bins are expected to be empty, no balls at all. Well, it's the total number is linear, so I can sum up for every bin, are you empty or no? And so by linearity of the expectation, the expected number of empty bins is the sum over all the bins, and for each bin, the probability that it is empty. That, of course, we can compute. It's the same probability for each bin. It's m times the probability that all the balls fall not in this bin, so it's the counter probability of the 1 over m and to the power n. And so if we set n to m, then we can use this approximation. I mean, it's really an inequality in both directions, but it's good enough, say, here for heuristic argument. Indeed, yeah, I'm including the error bounds here. You can take, I think it's 1 plus 1 over n minus 1. If you put that in, that's less than e, and then that's not true, the other way around. No, it converges to e. So there's a plus minus 1, but you can you can get a precise error bound like this. For this point, the derivation is not so important. It's an easy calculation, but the result means there's a 1. This is a 1 over e. For some reason, I've lost that here. There's a minus, right? So this is true, but then this thing has a minus, so it's e to the minus 1. Maybe I'll smuggle an exponent here. Okay, nobody can read this. There's a constant fraction of all bins that we expect to be empty. The expected number of empty bins is a constant fraction of all bins. And that doesn't seem to go well together with having in expectation a ball in each bin, right? This is somehow, we can't have both at the same time. And so one way to read this is, if you just look at expected values, is sometimes misleading, or they can give seemingly contradictory results, at least as long as you interpret expected value as that's going to likely happen, which of course here is not actually true. I don't know if I managed to trick you here or not, Chernoff bounds, of course, are true for binomials of any parameter. But if you look up what they actually say, it's the expected value, but then the plus minus, the error bound depends only on n, not on p. The bound you get from Chernoff bounds would say, okay, every bin is at most root n big with high probability, or square root n plus a tiny bit. And that's a true statement, but not so useful and very far away from saying most bins have one ball. All right? Okay. One way to resolve the puzzle would be to look at the birthday paradox, and we'll kind of use that later as an intuition. So it's useful to have one intuitive result there in mind. So birthday paradox is this scenario: you have people at a party, and the question is it likely that you have two people with the same birthday? Translated into our formal model, it's just the number n, the number of balls that you have to throw into a given set of bins, so that there is some bin that has two balls. And of course, this is not a hard cutoff, but we can say when is it at least probability 1/2 that you see a bin with two balls or more. The method to crack this or to approach this is to compute the counter probability. What's the probability that all the bins have at most one ball? And we go through the balls to determine that. So this is the first ball. It has all bins available. There's nothing that would make any bin over full. But for the second ball, there's the first bin that ball 1 picked that's no longer available without violating the constraint of having one ball per bin at most. So one bin is gone, but everything else is still possible. And the same pattern goes on for the ith ball. There's I bins that have been taken. They have to have exactly one ball because we don't allow more. And so you always have 1 over I over n, 1 minus I over n. So of course you can just go and compute that product for fixed values of n and m and see what the probability works out to. To make a more general statement, again, approximations help, and it's the Taylor series of the exponential function that helps us here. So just at x equals 0, you get 1 plus x, which is also the tangent, so it's always below. So this would always be a minus, I guess, but doesn't matter. It's an error term of the order of x squared as x goes to 0. If you plug that in for each of these terms, then you get, I'm using it reverse, right? This is what we have on the left. Now I'm bringing the error term to the other side, and I'm inserting into the exponent what I have here as the 1 plus x. And so these are all negative, so I'll get negative exponents, and I get an overall error term that you can compute if you care. And now we have an exponential, so we can sum up all the exponents, and that's just the sum of the first integers divided by m. So we get roughly as an exponent minus n squared over 2m. This assumes that n divided by m converges to 0. It's an asymptotic that's valid for this. And if you think about it, if n and m are close to each other, it's not going to be possible to avoid collisions. If you throw almost as many balls as bins, at the very least, if you throw more balls than bins, then you'll definitely have a bin with 2 balls. So this is clearly not going to make sense if n is approaching n is approaching m, but for smaller values of number of balls. And you can insert, well, when is this non-trivial, meaning not entirely close to 0 or 1? It's going to start out if n is 0 at 1, and then it's going to fall exponentially down, even worse, because it's squared, right? So it's very, very quickly falling down. And the range where it falls from essentially 1 to 0 is exactly when this is a small number. So when this is close to 1, So that's when n is roughly square root of m. Okay, specifically if you want to equate that to 1/2, you can calculate what the value of n is. And if you have the application from the birthday paradox, you get some 23 people, 22. Then you have a probability of 1/2 that there's 2 with the same birthday. And of course, the paradox is that you intuitively maybe think you need more people for that to be likely, because it's so many days in the year and you don't always meet people with the same birthday. But yeah, it's actually going to be a smaller number because it's not uniform, right? There's always, for obvious reasons, there's certain periods of the year where it's more likely to be born than others. But that's a different story. What it means for this paradox from before is we had 2 expected values, the expectation how many balls per bin and the expectation of how many empty bins. And the paradox only really came from somehow assuming that all bins simultaneously are close to their expectation. And that's just something you shouldn't really expect. It's not actually so likely that all bins are close to their expected occupancy. And that's true in many ways. All right. Let's do some real math that has applications for hashing. So one interesting question for hashing is if you just do this separate chaining, everything that ends up in one bin is a linked list, and you have to do the searches by reading through the linked list. What's the worst that can happen under this uniform hashing assumption? So we're still assuming the best possible world in terms of the hash values, but you're using essentially a hash table of the same size as the number of items, which is up to constant factors what you would use in practice. Maybe for chaining hashing, you'd even use a slightly smaller number of buckets, and for open addressing a bit bigger, but the hash table as a linear function of the number of items is the usual setup. And so this theorem says we should expect a weird number of balls in the most loaded bin. So you take the maximum, the fullest bin formally in our model is just the maximum over all j. Among the bins, and then xj. That's a random variable. You know what? This is popping up a few times. Maybe it's worth giving it a name. I don't think I've used the x hat anywhere. Let's call that x hat. And we're supposed to show that the bound is log n over log n. What a weird bound. Also, well, we'll come to the interpretation after doing the work, I guess. So you're maybe you can already think a bit about it. How can we prove this? We're just doing an upper bound here, but that's not where the intuition dies. I'll comment on that later. The probability that this largest xi is greater or equal than some specific threshold that we'll specify later, and this will eventually take this form. Let's try to compute that. And that seems, in general, seems a hard thing to compute because the maximum of random variables is a tricky beast. But because we're only interested in a tail bound, that it's bigger than some value m, when is the maximum bigger than some value m? Well, when any of the elements is bigger than value m. And so we can use the union bound to get, because they're also identically distributed, it's just n times the probability that any, yeah, okay, this is m nominally, but we set n to m, so it's the same. I'm going to keep m here because I think it's more logical. Okay, so we've reduced the problem to tail bound for the for any specific bin, say the first. And effectively, that's just a binomial distribution. But we're summing over this, so we can rewrite this, or you could express it as the sum over the probability weights for the binomial distribution. Another option is to say we take the union over all subsets of balls of the size that we want, at least m, and we take the event that the balls, all balls I in this set I land in the given bin. This is slightly more convenient than summing up the probabilities for x1 to be exactly a certain value, because now we can use union bound again. That's a union of events. So we're going to take the sum over all the events. They're all equally likely because everything's symmetric. So all we have to do is count how many subsets of size m are there out of the n balls, and that's a binomial coefficient, and choose capital M. And then we have the probability that any specific set land in bin 1. And, well, that's just 1 over m, the little m. To the power m, because we need that many of them. I'm just looking at those balls and forgetting about the others. Okay, that's the easy bit. Now let's use that n and m are the same. So really this is, let me just replace this here. Okay, let me not do it. So it's still visible. If we unfold this binomial coefficient, then we can simplify this a good bit. This is n factorial divided m factorial and n minus m factorial. That's just plugging in the definition. And then we have the n to the m down here. Now if you look at a bunch of terms, namely all these, there's an n factorial up here, and there's an n minus m factorial. So there's the largest terms are missing, but then we have the largest term up here m times. So the denominator will be strictly bigger, right? There's the same number of terms, and you can match them up. You have n and n, n minus 1 and n minus 2 and n, down to n minus m, and still n, and then the others are canceling exactly. And so if you remember this notation, I might have used at some point falling factorials. Clearly this green part is at most 1. So we can upper bound the overall thing by 1 over m factorial. And then again, we can use Stirling's approximation. Which is, in this case, we use the lower bound. So this is true, and then you can continue here to get e divided m to the power m. And then this other term here, because it's 1 over m factorial, we get a 1 over this 2 pi m square root. Again, that's less than 1, so we can just drop it if we want to continue our inequality. So if we can, if you go back, this was the probability that a single bin is larger than m. If you look at that function, if you make m big enough, that's going to drop very rapidly, right? Because this power m here, we divide by m first, and then it soon gets this below 1, and then the power m just goes exponentially down. We're using this in the union bound up here, so n times the whole thing. And that's the desired probability. So the probability that our x head is at most m will be n times this thing. So we would like this to be essentially 1 over n, then or smaller. Then the overall probability that we get by multiplying by n will be an interesting bound. And of course, we want it substantially smaller than 1 over n if we want to prove this high probability bound. So what can we plug in? Well, we need, I think it's still useful to do this kind of side calculation. So what would you have to pick for m for that to match? Well, if you set m to ln n divided ln log ln n, what happens? We get e divided this stuff and then to the power m. So I'm going to rewrite the whole thing as x blog. Now we can pull the m out, so it's factor m up here, and then log of e, which is 1, and then minus ln m. And if you insert what m is now, you get the ln n that becomes the 1 over n. I'm missing one minus here, right? Okay, there's a minus in total. And what's left from the rest is much smaller, because we have a minus ln n. And then here we have again so from the first term, you get roughly this 1 over n. Now for this, I wouldn't have needed the log, right? Okay, let's continue with the proper calculation. If you want to show the high probability bound, we want that the probability up there, that x head, is greater or equal than some threshold m. We want that to be big O of n to the minus d for some number. And so this we can upper bound with our bound from before, n times this guy. And so if we plug in this m with the factor c in front, then we have e to the c. That's from this part here, ln divided ln n. That's from the 1 over m. And then we have the power. Now we still got to do the x block trig. But let's try to do it carefully this time. So we take the log of this, that's an ln n for the first term. Then we get, so this, we'll pick c greater than e, so that this is less than 1. So that we can drop from the equation. Then we have the log of this whole term, we'll have this in front as a factor. And then log of the inner term. And then you have to keep a log of things. And now we're splitting off this, this term in here, right? And what you'll see is the ln n here with the log n cancels with that. No, not yet. No, it doesn't yet. So we get ln n, the log of log, that's a triple log. We'll only do this once, guys. ln n. That's from the first part. And then we have a negative term with this minus log n. And that's going to get the c ln n. And now I'm pulling this behind here. Then we have the log n from the denominator here, and we have the old denominator, log n. At least these cancel. That was that. So we have this log and this minus c. Those combine. Where would the factor 2 come from? And we have this lovely term here still. And now we're going to pull this out. Then that becomes an n to the 1 minus c times the exponential of this part, what's left. Yep. All right. This is going to get smaller and smaller. We take triple log and divide by log, so it's a little O of n in the end. And so it's going to be less than 1 for a large enough n. And so we'll also have so I'm not buying my my calculation here. I lost some term somewhere. There's if this was all there was, it would still be n to the power of this thing. That wouldn't completely go away. Okay, we'll borrow one more minus log n. So I'm gonna do a minus log n plus log n. So we have 2 log n up front here. And then we have an n log n minus 1. That's one way to show it. So this is going to be less than 1 for large enough n. So the whole thing gets negative. And then exp of a negative thing eventually becomes less than 1. Okay, so key step was inserting plus minus 0, but that's why we get the factor 2 up front here. So for large enough n, the overall thing is n to the 2 minus c. And now you see c was the constant in front of m. So for every, remember that with high probability bound says for every polynomial decay you want for the probability, there is a constant in front of the big O term that makes that true. And that's what we've shown here. So whatever d you want here, you can pick a c that's small enough so that this is less than this if you pick a c greater than d plus 2. Okay. Lengthy proof. What does it mean? First of all, you can strengthen the analysis with different techniques. What I showed you was still elementary calculations. If you don't lose your terms, what we used was really just union bound and some simple asymptotic tricks. You can show with other techniques that you actually get an asymptotic statement. First of all, what we've shown as an upper bound is also a lower bound. if you throw enough balls into bins, the fullest bin will have that exactly log n over log n behavior, which is still a bit weird. It popped out in the analysis where essentially we needed this to cancel terms. So what did the log do really? It canceled this log term here so that you get a minus c log n term. That's an algebraic reason why the log n shows up, but it doesn't explain intuitively why that's the case. And if you have a slightly bigger number of balls than bins, then you get this factor alpha in here, but the main shape remains the same. So in a sense, even under this uniform hashing assumption, if you care about the worst possible query time, hashing is not much better than a binary search tree, just a tiny bit. But of course, it's only for the worst bin. And the second is, you often study hashing with expected costs only, and that's missing a little bit the long tails. There's a big difference here between the average bin and this worst bin. All right. But of course, the bigger caveat is this uniform hashing assumption, which is not always realistic. I wanted to just mention without any further proofs, if you haven't seen this power of two choices idea, this sounds like the answer is known and there's nothing you can do. If you use hashing, you're going to have some bin that's at least roughly log n full. But that's not quite true if you use more than one hash function. If you use two hash functions and always check which is the smaller, the least loaded bin of the two, then immediately you get a drop to log n instead of log n, an exponential improvement. If you could do more than two hash functions, this only changes the constant, so that's not much more is happening there. The analysis for this is doable, but takes more time. So if you want to see it, it's explained nicely in their book. But the idea is worth keeping in mind. If you just take the less loaded bin of two random ones, then you get much sharper concentration. There's a last balls and bins problem. Probably you've seen this one before too. It's called the coupon collector problem. So you have your favorite collectible items. They come in packs. You have to buy the blindfolded pack. You don't know which one you get. It's uniform. How many packs do you have to buy until you get all the collectibles? In balls and bin language, how many balls do you have to throw so that every bin gets at least a ball? Then you've collected that bin. We can analyze this by saying SI is the number of balls that we need to reduce from I empty bins to I minus 1. So I could throw any number of balls into bins that already have a ball, and I'm counting those, but they don't get me closer to having all bins covered. But once I cover with my new ball the first empty bin, the first new empty bin, I stop counting in SI. And so the total number of balls I have to throw until I've collected all bins is the sum of all these. And the indices are reversed, right? You start with everything empty, so the initial SM will always be just deterministically 1. But from then on, it's random. You could throw things in the occupied bins again, or you could be lucky and get a new thing. Each of these is a geometric random distribution because you're essentially flipping a coin. You have the occupied bins, that's one option that the outcome can be, and you have the others. So you're flipping a coin until you for the first time see the outcome hit one of the empty bins. The PIs are different, right? It gets less and less likely to hit a free bin. But the expectation is always 1 over the probability for a geometric random variable. So it's easy to memorize and reuse here. So we can just compute the expectation. How many balls do you have to throw to get all bins covered as the sum of the expectations of these SI, which is their inverse probabilities. And that just adds up to m times harmonic number m, or m log n roughly. This you've probably seen before. You can also compute the variance in roughly the same way, because these SI are independent. They're not identically distributed, but they're still independent. And so the sum of the variance of a sum of independent variables is the sum of the variances. And if you do the math here, it gets a bit more tricky with the summations, but you can show that the variance is quadratic, and so the standard deviation is linear, which means of lower order term than the expectation. And that was enough with Chebyshev's inequality to get some concentration, in the sense that if you make n big enough, you'll see this random S converge to the expectation in probability at least.